13 billion years ago, the universe committed what can only be described as a cosmic crime. It built galaxies too early, massive, bright, and mature, long before the laws of physics said such things could exist. The James Webb Space Telescope didn't just glimpse them, it caught the cosmos disobeying its own timeline. At that epoch, the universe was barely 500 million years old, a cosmic infant just beginning to cool from the heat of its birth. Hydrogen still drifted like fog, unlit by stars. Dark matter scaffolding, which modern cosmology says is required to form galaxies, was only beginning to take shape. Yet in this fog, Webb found light, hundreds of points glowing in deep red, the signature of something impossibly ancient and impossibly large. 300 galaxies, each radiating with the luminosity of billions of stars, appeared in the telescope's infrared eye. They were not small sparks or primitive clusters. Some rival the mass of the Milky Way itself. According to the LCDM, lambda cold dark matter, model, the framework that has guided cosmology for decades, such galaxies shouldn't have existed for another billion years. The discovery stunned the astronomical community. For decades, scientists had constructed elegant models describing how the cosmos assembled. Small proto-galaxies forming first, merging slowly into larger ones, following the steady hand of gravity. But Webb's data told a story that unfolded at impossible speed, as if the universe had skipped entire chapters of its own evolution. Imagine an infant speaking fluent sentences moments after birth. That's what these galaxies represent. Their existence implies that matter organized itself, ignited, and matured in a fraction of the time predicted by physics. Each red point on Webb's image is a contradiction wrapped in starlight. The signal is not ambiguous. Infrared wavelengths reveal the unmistakable stretch of time. Light that has been traveling toward us for 13 billion years, stretched and reddened by the expansion of space. What we see today are ghosts of the cosmic dawn. Galaxies that burned bright when the universe was only 4% of its current age. At first, researchers suspected an illusion. Perhaps these were smaller, nearer galaxies disguised by dust. Perhaps active black holes were producing the light. But the spectral patterns, narrow, distinct, consistent, insisted otherwise. The energy came from vast collections of stars, not isolated sources. One researcher described opening the data set as watching the universe confess. The galaxies weren't faint or marginal detections. They blazed. Their brightness implied stellar masses of tens of billions of suns. That alone violated every timeline built into current cosmological equations. If this discovery holds, and multiple teams now confirm it, it forces a question more profound than any. Since the expansion of the universe was first measured, have we misunderstood how the cosmos grows? These galaxies are not just statistical anomalies. They are conceptual detonations. They suggest that gravity, star formation, and dark matter behave differently in the beginning. That the infant universe might have been far more efficient, dense, or chaotic than we believed. Even more striking is their color. Webb sees them as deep crimson smudges, glowing in wavelengths invisible to the human eye. That red hue is both a measurement and a metaphor. It tells us how far back we're looking and how stretched the light has become across billions of years of cosmic expansion. Each shade of red is a timestamp, a record of how quickly space has been pulling everything apart since the Big Bang. To detect such faint light, Webb stares at seemingly empty regions of space for hours, even days. In those voids, entire galaxies emerge, tiny, perfect dots whispering across eternity. Among them, these 300 stand out not because they exist, but because they shouldn't. If they are genuine, the implications ripple outward. The physics governing galaxy formation, the rate at which matter clumps, the timeline of dark matter halo growth, and the history of reionization, all of it would need revision. Even the calibration of cosmological simulations, which underpin our understanding of the observable universe, would need rewriting. Astronomy thrives on paradox. Each generation of telescopes reveals that nature is stranger than equations predict. But this is different. This is not a minor adjustment. It's a fundamental breach. It's as though the cosmos itself is asking whether we ever truly understood its youth. The galaxies may be distant, but their message is immediate. The early universe was not slow, gentle, or patient. It was restless, forming structure in a burst of creativity that defies everything we thought we knew about time and matter. In the coming sections, we'll follow this story the way a scientist would, through data, through error bars, through disbelief, and eventually through re-examination of the very equations that describe existence. Because to grasp why these galaxies matter, one must first understand how the universe was supposed to behave, and why it didn't. The cosmos has spoken, in a language of red light and broken rules. And for the first time in human history, we're close enough and clever enough to listen. In December 2021, a new kind of eye opened above Earth's atmosphere. The James Webb Space Telescope was not just another observatory. It was a time machine engineered to look so far and so deep that its images would expose the first pages of the universe's history. Its gold-plated mirrors, 18 hexagons working as one, were tuned to infrared light. The faint glow stretched across billions of years of cosmic expansion. Where the Hubble Space Telescope saw starlight, Webb would see the embers of creation itself. 6 months after deployment, its first deep-field images began to arrive. What looked to the untrained eye like black nothingness erupted into thousands of red points. Each was a galaxy, ancient beyond imagination. Among those pinpricks, a team at the University of Missouri noticed something odd. Several hundred objects glowed brighter and redder than any theoretical model could justify. They were not random noise. Their signals were sharp, consistent, and undeniably real. Thus began the mystery of the 300 impossible galaxies. The team was surveying 4 patches of sky, areas intentionally chosen for their apparent emptiness. By removing the clutter of nearby stars and galaxies, they could stare deeper into the universe's past. Using Webb's near-infrared camera, NIRCam, they collected photons that had been traveling since the universe was 500 million years old. When the data were processed, the software flagged hundreds of unusually bright red sources. Each dot represented light so faint that it took hours of exposure for even a few hundred photons to reach Webb's detectors. And yet those meager signals contained stories written across 13 billion years of expansion. Every photon was a survivor, having crossed space that itself was stretching the entire time it traveled. When the first false color composites were rendered, the screen looked like spilled rubies across velvet. The researchers expected to find a few modest candidates, perhaps 10 or 20 small proto-galaxies consistent with standard cosmological models. Instead, they found hundreds, and they were too bright. Brightness means mass. Mass means billions of stars. But there hadn't been enough cosmic time to make billions of stars. Something was off. To understand what Webb revealed, one must recall how light behaves in an expanding universe. As space stretches, the wavelength of light stretches with it. Blue light becomes red. Red becomes infrared. And eventually, if it travels long enough, it slips beyond what human eyes can see. This phenomenon, cosmological redshift, is not just a curiosity. It is the ruler by which astronomers measure time. When Webb detects light at extreme infrared wavelengths, it's observing events from when the universe was only a few % of its current age. By measuring how much the light has stretched, scientists calculate how long it has been traveling. For these galaxies, that number exceeded 13 billion years. Each detection corresponded to a redshift between 7 and 10, placing them a mere 500–700 million years after the Big Bang. That should have been an era of small, faint galaxies, if galaxies existed at all. Instead, Webb recorded massive, mature systems shining like cosmic cities already built and thriving. For decades, the Hubble Space Telescope defined our vision of the deep universe. Its ultra-deep field image revealed galaxies from when the cosmos was less than 1 billion years old. But Hubble's instruments were tuned to visible and near-ultraviolet light. By the time the earliest galaxies' photons reached us, That light had been stretched far beyond Hubble's range. They were effectively invisible. Webb was designed precisely to overcome that blindness. Its mirrors, more than twice Hubble's diameter, collect 6 times more light, and its detectors are sensitive from 0.6 to 28 micrometers. That range captures the glow of objects whose light left them before our planet even existed. In those wavelengths, Hubble's darkness becomes Webb's revelation. The irony is striking. For 30 years, astronomers stared into what seemed like empty sky, unaware that ancient giants were shining right there, just in a color no one could see. When the Missouri group first plotted the brightness curves, disbelief dominated the room. Every model said these galaxies should be at least 1 billion years younger than their calculated ages. To be sure, the team applied multiple checks, comparing colors through various infrared filters, estimating distances using the dropout technique, and ruling out nearer dusty galaxies masquerading as distant ones. The results held. Each candidate passed the tests for extreme distance, and the sheer number, around 300 across a small patch of sky, implied that the early universe was teeming with large structures, not sparsely sprinkled with small ones as previously thought. The implications were immediate and unnerving. If this sample was representative of the whole sky, then early galaxy formation was not a rare accident. It was a rule the current theories failed to predict. Under the lambda cold dark matter model, structure in the universe builds gradually. Tiny fluctuations in density become small clumps of dark matter. Those clumps attract gas, form dwarf galaxies, and slowly merge into larger systems. By 500 million years after the Big Bang, the model predicts mostly small, faint galaxies, cosmic seedlings still taking root. Yet Webb's detections show mature galaxies already heavy with stars, their light output matching systems billions of years older. The data imply that star formation, gas collapse, and dark matter clustering all happen 10 times faster than any simulation allows. It is as if someone pressed fast forward on cosmic history. In science, discovery often arrives not as a shout, but as silence, the kind that follows when equations and evidence refuse to meet. The lead astronomer on the project described staring at the dataset in disbelief. "We kept asking what we had done wrong, but the numbers didn't change. The galaxies were there. They checked calibration files, repeated photometric corrections, and compared their pipeline with independent teams analyzing other Webb surveys. The anomalies persisted across datasets and instruments. Different researchers, different software, same impossible result." That was when the tone shifted, from error hunting to paradigm testing. Webb's strength lies not only in its resolution, but in its patience. By holding its gaze on a single patch of sky for up to 12 hours, it collects every stray photon that drifts into its detectors. This relentless attention reveals what no ground-based telescope could ever see: galaxies whose light is fainter than a candle seen from the moon. Those photons, stretched across eons, carry within them the fingerprints of the early cosmos. From their wavelengths, astronomers derive temperature, composition, and velocity. From their brightness, they infer stellar populations. Each measurement adds a brushstroke to a painting of creation itself. Webb was designed to answer questions about the universe's infancy. Instead, it has raised new ones, questions that cut to the foundation of cosmology. When the numbers were tallied, the picture was clear. Roughly 300 candidate galaxies appeared within the survey area, each at distances corresponding to a time before the universe should have had such complexity. Scaled to the full sky, that suggests tens of thousands of similar systems may exist. If confirmed, this means the cosmos built large-scale structure almost immediately after the first atoms formed. The early universe was not an empty canvas. It was a workshop already busy with construction. In a single set of observations, the James Webb Space Telescope turned the cosmic timeline inside out. What was supposed to be a quiet, starless dawn now looks like a crowded metropolis blazing with newborn suns. The universe, it seems, didn't wait patiently for the laws of physics to permit life and light. It improvised. And as every scientist now realizes, Improvisation at a cosmic scale demands new physics, or a new understanding of the old ones. When scientists first modeled how the universe should evolve after the Big Bang, they built those equations on a foundation of patience. Gravity was slow, cautious, deliberate. Matter was supposed to gather over billions of years, forming stars and galaxies step by step. Yet, what Webb found belongs to a universe in a hurry, a cosmos that seems to have skipped the slow rehearsal and leapt straight to the finale. According to the lambda cold dark matter model, the architecture of everything we see today began as tiny fluctuations, ripples in the density of matter spread throughout the newborn universe. Dark matter, which interacts only through gravity, formed invisible halos that acted as scaffolding for ordinary matter. Hydrogen and helium gas then fell into these gravitational wells, cooled and condensed into stars. Small galaxies formed first. Over cosmic time, they collided and merged, building progressively larger systems. This bottom-up growth, hierarchical structure formation, is the central dogma of modern cosmology. But Webb's galaxies disobeyed that order. They appeared fully grown in a universe too young to permit it. It's as if skyscrapers rose overnight before the foundations were poured. In the early universe, physics imposes strict timing. Gas must cool before it collapses. Stars must ignite before they enrich surrounding clouds with heavier elements. Dark matter must clump before it can anchor galaxies. Each stage depends on the previous one, and each requires time. Computer simulations based on LCDM suggest that, by 500 million years after the Big Bang, the largest galaxies should have contained perhaps a few 100 million stars. What Webb sees instead are systems holding tens of billions, masses comparable to the modern Milky Way. That's not a small discrepancy. It's a 1,000-fold acceleration of cosmic evolution. If these measurements are correct, something about the universe's initial conditions or its physical laws operated faster, or differently, than expected. Either gravity gathered matter with unnatural efficiency, or star formation raced ahead of schedule. In both cases, our model breaks. Dark matter halos are the skeleton of the cosmos. They determine where galaxies form and how fast they grow. Simulations show that, early on, these halos were small, only a few million solar masses, and took hundreds of millions of years to merge into larger ones. A Milky Way-sized halo shouldn't exist until at least 2 billion years after the Big Bang. Yet, if Webb's galaxies truly possess such mass, then their halos must have formed 1 billion years too soon. That implies gravity, or the behavior of dark matter itself, acted more aggressively in the past than LCDM predicts. Perhaps dark matter wasn't cold after all. Maybe it moved faster, clumped differently, or even interacted weakly with ordinary matter. Each possibility would rewrite the physics we use to simulate the universe. Another contradiction hides within the starlight itself. When astronomers analyze a galaxy's light, they can estimate the age of its stars by studying the color distribution. Blue light means youth. Red light means age. In these early galaxies, the mix suggests stellar populations already hundreds of millions of years old. That means star formation began even earlier, possibly only 200 million years after the Big Bang. But that period was supposed to be the cosmic dark ages, when no stars yet burned and hydrogen gas filled space like fog. To form mature stars so soon, the universe must have achieved the impossible, creating, igniting, and recycling stellar generations faster than the time it took for hydrogen atoms to cool. Even if star formation began at record speed, heavy elements like carbon, oxygen, and iron, which are forged inside stars and expelled in supernovae, shouldn't have existed yet. Yet the spectral data hint at their presence. The galaxies glow with the fingerprints of metals that shouldn't have been there for hundreds of millions of years. This creates a chronological paradox. The galaxies are older than the time available for them to age. Physics imposes a natural braking system on star formation known as feedback. When massive stars form, they emit intense radiation and stellar winds that push gas away. When they die as supernovae, They scatter energy that heats and disperses the remaining gas. These mechanisms prevent galaxies from turning all their material into stars too quickly. They act like a thermostat, ensuring that star formation occurs over billions of years, not millions. But Webb's galaxies appear to have ignored that limit. Their inferred star formation rates, hundreds of solar masses per year, suggest they formed stars 10 to 20 times faster than any galaxy we observe today. For that to happen, feedback must have been weaker, delayed, or altogether different in the early cosmos. Maybe the first gas clouds were denser and could resist stellar winds. Maybe the lack of heavy elements allowed radiation to escape more easily, letting star formation proceed unchecked. Either way, the laws that govern galactic growth today may not have applied in the same way back then. The LCDM model doesn't just predict timing, it predicts numbers. At any given epoch, there should be a calculable number of galaxies of each size. Finding one or two massive galaxies at early times could be dismissed as statistical flukes. Finding 300 is impossible to ignore. To produce so many so soon, the universe must have been much more efficient at concentrating matter. But that efficiency violates the statistical spread of density fluctuations observed in the cosmic microwave background, the leftover radiation from the Big Bang. That background is smooth to 1 part in 100,000, tiny ripples, not giant waves. It's from those ripples that all structure formed. For the early universe to have built 300 massive galaxies, those initial ripples must have been stronger than we see. Either the background data are missing something, or the physics of how ripples grew has been misunderstood. Science thrives on anomalies, but this one cuts to the timeline of everything. If galaxies assembled this quickly, it suggests the universe's first billion years were far more dramatic than our equations allow. Ionization, dark matter clustering, star birth, and metal enrichment must have all occurred in a condensed burst, an accelerated adolescence for the cosmos. It also hints that time itself, as measured by our interpretation of cosmic expansion, might be slightly off. Some physicists propose that if dark energy behaved differently in the early universe, expansion rates could shift, altering our inferred ages. In that case, these galaxies might not be as old as they appear, but they'd still be far too old for comfort. Every few decades, astronomy faces a crisis. The discovery of cosmic acceleration in the 1990s forced physicists to invent dark energy. The missing mass problem led to dark matter. Now, Webb's discovery threatens the very framework that unites those two ideas. The LCDM model has survived every test. Until now, because it elegantly explains everything from the large-scale structure of galaxy clusters to the temperature patterns. In the cosmic microwave background, it is the language of cosmology. But languages evolve, and sometimes words fail to describe new phenomena. Webb's 300 galaxies are that failure written in red light. They tell us the universe was not content to follow its own rules. It built too fast, too soon, too bright. And now, every cosmologist must confront a humbling truth. Perhaps the universe has always known something we do not. Before those galaxies blazed into existence, the universe endured a silence so absolute that even light could not travel freely. After the Big Bang, space was a storm of energy and particles, expanding, cooling, and eventually calming into a transparent cosmos. But for hundreds of millions of years after that transition, darkness ruled everything. This period, known as the Cosmic Dark Ages, was not poetic exaggeration. It was literal. There were no stars, no galaxies, and no light. Only hydrogen atoms drifted through an ocean of darkness, absorbing every photon that tried to move through them. In that early time, the temperature of the universe had fallen enough for electrons and protons to combine into neutral hydrogen. The fog that once scattered radiation cleared, allowing the first photons from the Big Bang, the cosmic microwave background, to stream across the cosmos. Then for the first time space became transparent. But it was a transparency without illumination, an empty theater waiting for its first spark. Gravity was already at work, pulling the densest pockets of hydrogen into invisible knots of dark matter. These knots, though unseen, would become the scaffolding for every future galaxy. If one could have watched this slow choreography unfold, it would have looked like nothing at all. The universe was utterly black, yet underneath, gravitational attraction never stopped pulling. Over millions of years, those invisible wells of dark matter deepened. Gas flowed toward them, compressing, heating, and fragmenting. The density grew until, in one of those dark clouds, the first nuclear fire ignited. A star was born, and the Dark Ages ended. The first stars were unlike any that exist today. Made only of hydrogen and helium, they were enormous, hundreds of times the mass of the Sun, and burned at unimaginable brightness. They lived quickly, spending their fuel in just a few million years before collapsing in titanic explosions. Each supernova hurled heavier elements like carbon and oxygen into space for the first time. Those elements would seed new generations of stars, enriching the gas that followed. In those explosions, the universe finally gained color and chemistry. The ignition of those first stars changed everything. Their ultraviolet radiation ionized the surrounding hydrogen, carving bubbles of transparency through the cosmic fog. These glowing pockets grew and merged, slowly ionizing the entire universe. For the first time since the Big Bang, light could travel freely again. The cosmic dawn had arrived. And yet even that process should have taken time. From recombination to the first stars, the universe needed at least a few 100 million years of quiet buildup. Star formation was supposed to begin around 200 million years after the Big Bang, followed by small, scattered clusters of young stars. Only later would these small assemblies merge to form the first galaxies. At least that's what the equations insisted. The light James Webb now observes seems to tell a different story. The galaxies that appeared 500 million years after the Big Bang are far too massive to have formed through those slow, sequential steps. Their presence implies that the Dark Ages ended more abruptly, as if entire regions of the cosmos lit up almost overnight. Perhaps gravitational collapse in those regions happened with extraordinary efficiency, or maybe something else entirely. Something still unknown compressed matter more violently, creating massive galaxies before the cosmic fog had even cleared. The irony is that astronomers only know this period indirectly. No telescope can yet see through the thick hydrogen that filled space before reionization. Everything we understand about that time comes from simulations and from observing what came next. The first luminous objects bright enough to pierce the fog. Every data point we gather from Webb is like hearing an echo of a sound we never witnessed. We can't see the ignition itself. We can only trace the glow that followed. If those 300 galaxies truly existed at that early epoch, they must have formed almost immediately after the first stars were born. That means multiple generations of stars had already lived, died, and recycled their material within a few 100 million years. The efficiency required is staggering. For comparison, the Milky Way has been forming stars for over 13 billion years, and it still hasn't reached the stellar density implied by some of these early systems. When scientists attempt to model this mathematically, the numbers refuse to fit. The equations demand more time, more cooling, and more structure formation than the universe had back then. If gravity alone cannot explain such rapid assembly, perhaps another mechanism contributed. Some researchers have begun to explore the idea that turbulence, magnetic fields, or even exotic particles might have accelerated gas collapse in the early universe. Others suspect that early black holes forming directly from collapsing gas might have acted as gravitational anchors around which matter could collect quickly. Whatever the cause, the outcome was the same. The Dark Ages ended far sooner than predicted, and the universe began constructing massive galaxies long before it was ready. The first light that emerged from that darkness wasn't gentle. It was fierce and transformative. Each of those primordial suns burned hot enough to reshape the chemistry of the cosmos. Their ultraviolet radiation stripped electrons from hydrogen, turning opaque gas into transparent plasma. As this ionization spread, the universe transitioned from a cold fog to a luminous sea. Within only a few 100 million years, regions that were once black emptiness had become brilliant clusters of fire. What the James Webb Telescope now captures is the afterglow of that transformation. When its sensors detect faint red smudges at the farthest edge of vision, they are seeing light from those first cosmic cities, the earliest places where gravity and radiation negotiated the rules of creation. The Dark Ages ended not with a whisper but with a blaze, and it is that blaze, stretched across billions of years, that now reaches our eyes. The astonishing part is not merely that light found its way out of darkness, but how quickly it did so. In a universe governed by patience, these galaxies represent impatience incarnate. They are evidence that something in those first few 100 million years was far more energetic, far more efficient, and perhaps far more mysterious than we ever imagined. The night that once defined the cosmos was short-lived. The fire that followed has never gone out. The discovery of those galaxies did not happen by accident. It was the result of an observation technique refined over decades, a combination of patience, precision, and a deep understanding of how light carries history. When the James Webb Space Telescope looked into what seemed like empty space, it wasn't photographing brightness. It was collecting age. Every photon caught in its detectors had traveled for billions of years, redshifted and stretched by the expansion of the universe. Those faint pulses of infrared radiation were not just remnants of distant suns. They were messages written across time. The key to recognizing those ancient galaxies lay in how hydrogen interacts with ultraviolet light. Hydrogen, the most abundant element in the cosmos, absorbs light at a specific wavelength, creating a distinct fingerprint known as the Lyman limit. When astronomers take multiple images of the same region using different filters, they can see which wavelengths an object disappears from. If a galaxy vanishes in the bluer, shorter wavelengths but appears clearly in redder, longer ones, that dropout indicates its light has been stretched by immense cosmic distance. This is the dropout technique, a kind of cosmic detective work. It doesn't just reveal where galaxies are, it reveals when they are. Using this method, astronomers examined more than 500 square arc-minutes of sky captured by Webb's near-infrared camera. They carefully compared each wavelength band, searching for the characteristic dropout signature that marks extremely distant galaxies. Every red dot that survived this filtering process was a potential time capsule from the early universe. When the analysis was complete, the researchers had identified roughly 300 of them, all showing that same distinctive pattern: gone in the blue, blazing in the red. The further back in time one looks, the more stretched the light becomes. For these objects, the degree of redshift implied distances so vast that the light we detect began its journey more than 13 billion years ago. Each point was then analyzed for brightness across several filters. If it glowed brightly in one infrared range but dimmed sharply in another, astronomers could estimate its redshift value. The more stretched the wavelength, the older the light. But redshift alone wasn't enough. To confirm these were not merely nearby dusty galaxies imitating ancient ones, researchers used Webb's mid-infrared instruments to look deeper. Dust has a different spectral signature. It scatters blue light and glows in specific mid-infrared bands. The candidates Webb found did not match the dust profile. They behaved like genuine distant galaxies. What made this so convincing was the consistency. Across independent teams, working on separate datasets from different sky regions, the same result appeared: redshift values between 7 and 10, corresponding to galaxies that existed only 500 to 700 million years after the Big Bang. Even allowing for uncertainties, too many objects fell into that same improbable range. The universe, at that point in its history, should not have been so crowded with massive structures. Yet the data insisted otherwise. To ensure accuracy, astronomers also analyzed each object's spectral energy distribution, the unique pattern of light intensity across multiple wavelengths. This pattern acts like a fingerprint, revealing temperature, composition, and distance. For the Webb candidates, these distributions aligned perfectly with what one would expect from young, star-forming galaxies at extreme redshifts. Their light peaked in the infrared, a hallmark of stellar populations formed from hydrogen and helium, burning with youthful ferocity. As data accumulated, one unexpected feature began to dominate the analysis: the redness. More than 80% of these galaxies were what astronomers call extremely red objects. Their brightness was not uniform. It spiked dramatically in certain infrared wavelengths. The difference between their brightness in one filter and another often exceeded 2 magnitudes, meaning they were 6 times brighter in one band than the next. Such disparity could not be explained by simple distance or dust. Something intrinsic to their structure, perhaps temperature, perhaps an unusual mix of stars, was making them shine redder than predicted. This redness was crucial for another reason. It provided a way to separate the authentic from the imposters. The color pattern, when plotted, produced a sharp step known as the Lyman break. Objects showing this break at specific infrared wavelengths could be placed precisely on the cosmic timeline. Each break marked how much the light had stretched since emission. The greater the shift, the further back in time the light originated. Using this, researchers could categorize galaxies without direct spectroscopy, relying instead on how their brightness changed across Webb's filters. Still, there were doubts. Astronomers are cautious by nature, and extraordinary claims demand extraordinary verification. Could these red points be quasars, supermassive black holes feeding on gas and mimicking the glow of galaxies? Could they be closer, smaller systems cloaked in dust? To test this, scientists looked for variability, light fluctuations that quasars often produce. None were found. The red dots were steady, stable, unblinking. Their light was not the flicker of accretion. It was the collective glow of billions of stars. Another check came from gravitational lensing. Some of Webb's deep fields overlap regions where massive galaxy clusters bend light from behind them, magnifying distant objects. If the 300 galaxies were lensed, they might appear brighter and more numerous than they truly were. But when models of the gravitational foreground were applied, the magnification factors were modest, not enough to account for the population explosion. Even after adjusting for lensing, the abundance of these galaxies remained implausibly high. In the end, every cross-check pointed in the same direction. These were not artifacts, errors, or illusions. They were real structures, vast assemblies of stars born when the universe was barely out of infancy. Their existence demanded explanations that current cosmology could not yet provide. The dropout method had not only confirmed their age, it had revealed a hidden truth. The universe was building faster, brighter, and more energetically than anyone had anticipated. Each new observation refined the distances further. Some galaxies exhibited redshifts exceeding 10, placing their formation less than 450 million years after the Big Bang. That means the first generation of stars, the ones that ended the Dark Ages, had already given birth to mature galactic systems within a cosmic blink. The earliest known epochs of structure formation suddenly looked crowded, almost bustling compared to the empty void scientists once imagined. In Webb's data, these galaxies are mere pinpoints, faint red smudges against a black background, yet each represents a gravitational empire, billions of suns held together by forces that should not have had time to assemble. The methods used to find them are rigorous, mathematical, and precise, but the emotion they evoke borders on awe. In a universe governed by equations, the cosmos once again refused to behave like a solved problem. Every pixel in Webb's images is an argument against complacency. Each detection challenges the story that scientists thought they had already written. The dropout technique, once a quiet analytical method, has become the instrument of revelation. It has shown that the universe's earliest structures were not tentative sparks. They were roaring fires. And those fires, still glowing in infrared light, have carried their message for 13 billion years, waiting for a telescope capable of listening. Their nature defied every expectation. When the light curves were modeled, the galaxy's brightness translated into stellar masses of billions, sometimes tens of billions, of suns. That made no sense. In a universe only 500 million years old, there should not have been enough material or enough time to build them. The Milky Way, for comparison, took more than 10 billion years to reach a similar mass. Yet these early structures, born at the edge of time, already burned with the intensity of fully developed galactic systems. Their color told another part of the story. The redness was not just a measure of distance, but a clue to composition and age. The redder the light, the older the stars it contains, because older stars burn cooler and emit less blue light. When astronomers modeled the spectral energy distributions, they found that many of these galaxies contained populations of stars that appeared several 100 million years old. That meant that even before the universe was 500 million years old, star formation had already been happening for a considerable span of time. If the universe itself was 500 million years old, then these stars must have started forming when it was barely 200 million years past the Big Bang, almost immediately after the first atoms cooled. In a sense, the universe had no childhood. It went from birth to adolescence in an instant. The data suggested star formation rates that dwarfed anything observed today. Some of the galaxies appeared to be producing hundreds of stars every year, comparable to the most violent starburst galaxies known, but in an epoch when gas was still primordial. To do that, the gas had to collapse under gravity with extraordinary speed and efficiency. That shouldn't have been possible. The radiation from the first stars and the explosions of the first supernovae should have blown gas away, halting further star formation. Feedback mechanisms, nature's way of keeping galaxies in check, seem to have failed entirely. These galaxies were not small, chaotic clusters. Their luminosity profiles suggested organization, central concentrations surrounded by extended halos of light. Some displayed disk-like structures. Others hinted at spiral symmetry. This level of structure implies rotational stability, a balance between gravity and angular momentum. But forming that balance takes time and repeated mergers. To find it in galaxies this young meant that either mergers happened far faster than theory allows, or the conditions of early space favored order rather than chaos. The spectral signatures also hinted at metals, elements heavier than helium. Astronomers use the term metallicity to describe how enriched a galaxy's gas is with such elements, which are created only in the hearts of stars and spread through supernovae. Detecting metals in galaxies so early meant that at least one, and possibly several, generations of stars had already lived and died. That's an impossible timeline according to conventional models. Even if the first stars formed 200 million years after the Big Bang, they would need several generations to enrich the gas significantly. Yet here, in galaxies seen at a time when the universe should still be chemically pure, those signatures already existed. It suggested that star formation and destruction happened not slowly, but in explosive cycles. Birth, death, enrichment, and rebirth, all compressed into a few 100 million years. Astronomers tried to imagine how such systems could form so quickly. Perhaps the initial density of matter was higher in certain regions, allowing gravitational collapse to proceed more violently. Perhaps dark matter halos were denser and more compact than expected, gathering gas into deep potential wells that accelerated star formation. Or perhaps black holes formed directly from collapsing clouds of gas, anchoring early galaxies, and triggering rapid star birth through their immense gravity. Each hypothesis required bending the known laws of physics slightly, but none of them could account fully for the scale of what was observed. The energy output of these galaxies was staggering. Their ultraviolet luminosity suggested thousands of massive stars, each burning at millions of degrees. The collective radiation from so many young suns could have reionized vast regions of the early universe, transforming neutral hydrogen into ionized plasma and clearing the fog that once obscured everything. In that sense, these galaxies were not just products of the cosmic dawn. They were its architects. Their light may have been the force that made the universe transparent again. But that explanation carried its own problems. If these galaxies emitted enough radiation to reionize their surroundings, then the rate of reionization should match what we observe in the cosmic microwave background. It doesn't. The timing inferred from these early galaxies conflicts with the timeline measured from background radiation. Either the galaxies formed earlier than we think, or the universe's ionization history is more complex than our models describe. Every solution leads to new inconsistencies. The shape of their light curves also revealed something unusual about their stars. Many of them seem to be extremely massive, far larger than the stars that dominate galaxies today. These so-called population 3 stars, composed almost entirely of hydrogen and helium, were theorized but never observed directly. They would have been short-lived but intensely bright, capable of flooding their galaxies with ultraviolet radiation and jump-starting chemical evolution. If such stars really populated these galaxies, then Webb's detections might be the first indirect evidence that population 3 stars once existed. Their deaths would have seeded the cosmos with metals, paving the way for the complex chemistry that later formed planets, carbon, and life itself. There was another mystery in the data: the sheer compactness of these galaxies. Many appeared to be only a few hundred light-years across, yet they contained as much mass as galaxies thousands of times larger. That density defied explanation. To pack so many stars into such a small volume required gravitational pressures almost unimaginable. In such conditions, collisions between stars would have been common. The environments would have been violent: gas swirling, stars forming and dying in overlapping waves, black holes devouring matter at furious rates. The early universe, once thought to be calm and empty, now looked like a furnace. Some simulations began to reproduce aspects of what Webb saw. When researchers artificially increased the rate of gas cooling or reduced the effect of feedback, galaxies grew faster, closer to the observed data. But these adjustments were ad hoc, like patching cracks in a dam. They didn't explain why the universe would behave that way naturally. Others proposed that maybe our understanding of star formation at low metallicities was incomplete. That primordial gas, free of heavy elements, could collapse more efficiently because it radiated heat differently. Without metals to trap energy, cooling might have been faster, allowing gas clouds to contract sooner. That could have accelerated star formation in those first dark halos, creating bursts of stellar birth powerful enough to build massive galaxies in record time. Still, the numbers didn't quite fit. To reach the inferred masses, the star formation efficiency would have to exceed 50%, meaning half of all available gas turned into stars. In the modern universe, the efficiency rarely surpasses a few percent. Something extraordinary was happening in those early epochs, something that made gravity more ruthless and creation more rapid. It was as if the laws of physics themselves were more permissive in the beginning, allowing the universe to indulge in a brief, extravagant frenzy of formation before settling into the slower rhythm we know today. Each time astronomers thought they had accounted for one discrepancy, another appeared. The luminosities were too high. The masses were too large. The densities were too extreme. The metallicities were too advanced. These galaxies were not supposed to exist, yet there they were, real, measured, undeniable. The Webb telescope, with its mirror cold and patient beyond Earth's atmosphere, had revealed a cosmos that was both more beautiful and more disobedient than theory ever allowed. Their light was not just illumination, it was evidence that our picture of the early universe, once drawn with confidence, was missing entire chapters. These galaxies were not anomalies on the margins of cosmology. They were its correction notes, written in starlight, inviting humanity to start rewriting the story of creation itself. Scientists do not like contradictions, yet astronomy thrives on them. Every time the universe defies a rule, it offers a new one to discover. When the data from the James Webb Space Telescope revealed galaxies that should not exist, theorists across the world began rewriting equations and building new possibilities from the fragments of broken certainty. The goal was not to deny what Webb had seen but to explain it, to find within physics some hidden flexibility that could accommodate what appeared impossible. One of the first ideas revisited was the structure of dark matter. The standard model assumes it to be cold, moving slowly enough for gravity to draw it into dense halos where galaxies can form. But what if dark matter was warmer or more interactive than expected? If its particles moved faster, they could clump earlier, collapsing into compact structures that would seed galaxies much sooner than current models allow. Alternatively, if dark matter occasionally interacted with normal matter rather than remaining completely aloof, it might have accelerated the condensation of gas in the early universe, creating gravitational wells deeper and more efficient than simulations predict. Changing the behavior of dark matter, however, risks unraveling the success of the current cosmological model, which so elegantly explains large-scale structure. Adjust it too much, and the universe we observe today no longer forms correctly. Still, the data from Webb was persuasive enough to make some researchers willing to challenge that foundation. Others turned to baryonic physics, the behavior of ordinary matter. Perhaps the cooling of primordial gas was faster than we thought. In the young universe, metal-free gas could radiate heat through molecular hydrogen emission, a mechanism often dismissed as inefficient in the past. If this cooling was far more effective, then dense clouds might collapse to form stars in a fraction of the expected time. Combined with the absence of heavy elements, which in modern galaxies trap heat and slow collapse, the early universe could have been a perfect engine for rapid star formation. In that case, the galaxies Webb observed would not violate physics at all. They would simply reveal a version of star formation unmoderated by complexity, a raw, unrestrained process belonging only to the universe's youth. Some theorists looked even deeper, suggesting that the fundamental constants of nature might have shifted slightly in the earliest epochs. A small change in the gravitational constant, for instance, could dramatically alter the rate of structure formation. Others speculated about new fields or particles that temporarily increased the efficiency of matter clustering. A transient physics of the dawn. These ideas are difficult to test, but not impossible. The same data that introduced the paradox may, over time, contain the clues needed to resolve it. Another possibility emerged from the concept of black hole seeds. In current theory, supermassive black holes form gradually, starting from the remnants of massive stars. But if, in the early universe, vast clouds of gas collapsed directly into black holes without fragmenting, these direct collapse black holes could have served as gravitational anchors around which galaxies formed at record speed. They would have fed on surrounding gas, igniting star formation in violent bursts while simultaneously growing themselves. Such systems would explain both the rapid assembly of mass and the high luminosity of the early galaxies. Some of Webb's observations indeed show hints of compact, bright cores, potential signatures of those primordial giants. If confirmed, this would rewrite not only the history of galaxies, but also the origin story of black holes themselves. Yet each explanation, no matter how creative, opened new questions. If direct collapse black holes were common, why do we not see their remnants everywhere today? If dark matter behaved differently, why does it match modern observations so precisely? If star formation was faster, what stopped it from consuming all available gas? Every fix created a new fracture. A few scientists dared to suggest that perhaps the universe is not expanding exactly as we think. The relationship between redshift and distance depends on how expansion has evolved over time, governed by the mysterious influence of dark energy. If dark energy changed its strength in the early universe, stronger, then weaker, it could alter how we interpret redshifts. The galaxies might not be quite as far or quite as old as we calculate. This early dark energy hypothesis had already been considered as a potential solution to the Hubble tension, the discrepancy between local and cosmic measurements of the expansion rate. Now it found new relevance. Maybe Webb's galaxies were the fingerprints of a brief, intense phase of cosmic acceleration that shifted the timeline of everything. Others proposed that our interpretation of light itself might need revision. The standard photometric techniques assume that galaxies emit light in certain ratios across wavelengths based on known stellar populations. But what if the first galaxies contained stars so massive and so hot that their light distributions were different from any we've modeled? If population 3 stars dominated these systems, their ultraviolet output could mimic the brightness of much larger galaxies. In that case, the paradox might not lie in their mass but in our assumptions about their composition. The galaxies could be smaller, filled with massive, short-lived stars burning at impossible intensity, a universe of fireworks that faded quickly, leaving no trace but infrared echoes. A subtler line of thought questioned the idea of time symmetry itself. In quantum cosmology, some models predict that the early universe could have behaved as if entropy, the arrow of disorder, ran differently near the Big Bang. If the physics of thermodynamics was not yet stabilized, energy could have condensed into structure more easily. Matter might have fallen together before the usual constraints of entropy and radiation pressure took hold. This is speculative physics, but so is any idea born at the edge of time. Despite their differences, all these theories shared one goal: to preserve coherence between observation and understanding. The universe had delivered a riddle, and science was answering in the only language it knows: possibility. Every new model was an act of humility as much as imagination. The data from Webb forced researchers to confront how much of cosmology remains inference. Our equations, beautiful as they are, rest on limited glimpses through narrow windows of time. Now a wider window had opened, and the view was unsettling. The debate grew fierce. Some teams cautioned patience, reminding others that redshift measurements based solely on color are uncertain. Spectroscopic confirmation, the direct splitting of light into its constituent wavelengths, would be the ultimate proof. As Webb's spectrograph began its work, early results confirmed many of the photometric distances, but revised others downward. A few galaxies turned out to be closer and less massive than first believed. Yet the majority remained stubbornly ancient. The central mystery endured. What all agreed on was that the universe's first billion years were more active than any model predicted. Even if some of the galaxies proved to be less extreme, the population as a whole still implied an extraordinary burst of star formation and structure building. The cosmos was efficient, eager, and restless in its youth. It did not crawl toward complexity. It sprinted. And so scientists now find themselves standing at the edge of an old story rewritten. Perhaps the universe's laws have not failed, but merely revealed their deeper versions, visible only under the pressure of creation itself. The galaxies that Webb uncovered are no longer mistakes to be corrected. They are invitations to understand more profoundly. Each one is a laboratory of extremes, a fossil of physics under conditions we can never reproduce on Earth. In their defiance lies discovery. The same way past paradoxes led to relativity and quantum mechanics, this one may lead to a new understanding of how matter and time co-evolved. Theories rise and fall, but the light remains. The red smudges in Webb's images are not just distant galaxies. They are signposts marking where human knowledge must travel next. If those galaxies truly existed at such early times, their light did more than illuminate the darkness. It changed the very state of the universe. When the first stars ignited, they emitted immense amounts of ultraviolet radiation, powerful enough to strip electrons from hydrogen atoms, turning neutral gas into ionized plasma. This process, called rionization, transformed the universe from an opaque fog into the transparent cosmos we now inhabit. For decades, astronomers believed that rionization was gradual, a slow, patchy awakening spread across hundreds of millions of years. But the galaxies Webb uncovered suggest a far more dramatic scenario, one where light reclaimed the universe almost in an instant. Each early galaxy acted like a miniature furnace, pouring energy into its surroundings. When enough of these furnaces appeared close together, their bubbles of ionized gas began to merge, carving out vast clearings in the cosmic fog. If Webb's 300 galaxies are representative of what existed across the sky, then the early universe was not a tranquil landscape punctuated by occasional light, but a crowded metropolis of burning suns and radiating hydrogen. In such a universe, rionization could have completed far earlier than the models predicted. Light would have flooded the cosmos in a single turbulent surge. This idea is both elegant and problematic. The cosmic microwave background, the faint radiation left from the Big Bang, carries subtle imprints of when and how rionization occurred. Those imprints suggest the process ended about 1 billion years after the Big Bang, not half that time. If Webb's galaxies were as numerous and bright as they appear, they would have finished the job long before that mark. To reconcile the two timelines, something must be missing from our understanding of how early light interacted with its environment. Perhaps the galaxy's radiation escaped less efficiently than assumed. Dense clouds of gas could have trapped much of the ultraviolet energy, delaying reionization despite the intense local activity. Or maybe the galaxies burned in short, intermittent bursts, switching on and off like cosmic flares instead of shining continuously. The timing of reionization, it seems, depends not just on how many stars existed, but on how leaky their galaxies were to light. As Webb gathered deeper images, patterns began to emerge. Some of the earliest galaxies appeared surrounded by faint halos of diffuse emission, possible signs of the ionized regions expanding around them. Others displayed extended arcs of gas, glowing faintly in hydrogen's Lyman alpha line, a spectral fingerprint of reionization in action. These features were more than aesthetic curiosities. They were the universe caught in the act of transformation. For the first time, astronomers were not inferring reionization from models or remnants, but watching its architects directly. The intensity of the radiation implied a feedback loop. The galaxy's light ionized surrounding hydrogen, which reduced the density of gas available for new star formation. As regions cleared, galaxies within them could shine even brighter, their radiation traveling farther and igniting new bubbles of ionization beyond. It was a self-propagating wave of illumination, a cosmic chain reaction. In a sense, the early universe was performing a vast experiment in causality, light creating the conditions for more light. The balance between collapse and radiation determined how fast the universe transitioned from opaque to transparent, and Webb's findings suggested that the process leaned heavily toward speed. Yet the consequences of such rapid transformation would have been profound. A universe that reionized too quickly might have disrupted the formation of small galaxies, whose fragile gas reservoirs could have been stripped away by the intense radiation. The result would be a cosmos dominated early by a few powerful systems, exactly what Webb seems to show. If this interpretation is correct, then the first massive galaxies didn't just coexist with smaller ones. They suppressed them, monopolizing the universe's resources and reshaping the landscape of cosmic evolution. The hierarchical model, where small structures merged into larger ones, may have been inverted, large galaxies forming first, smaller ones struggling to survive in their glare. Reionization also affected chemistry. When hydrogen atoms lost their electrons, they altered how gas cooled and condensed. Ionized regions cooled more slowly, changing how new stars could form. That means the galaxies that triggered reionization also dictated the properties of later generations. The fingerprints of that process still echo in today's galaxies, including our own. The Milky Way's oldest stars, enriched with specific ratios of elements, may carry chemical memories of that chaotic epoch. As observations continued, astronomers began to realize that reionization was not a single event but a mosaic, a patchwork of bright, cleared regions expanding through a universe still thick with neutral gas. Some areas likely reionized early, perhaps driven by clusters of massive galaxies, while others lagged behind for hundreds of millions of years. The Webb detections likely represent the first nodes of this network, the earliest islands of transparency in a dark sea. Between them, vast voids of unlit hydrogen would have remained, waiting to be pierced by light. In that sense, the cosmos during this era resembled a night sky before dawn, points of brilliance scattered across an otherwise unbroken black. Understanding this balance between light and darkness requires connecting Webb's infrared images to other observations, like radio signals from neutral hydrogen. Projects on Earth, such as the Square Kilometre Array, aim to map those signals, revealing where reionization began and how it spread. When combined, these data will turn the story of cosmic dawn from conjecture into chronology. And if Webb's galaxies are indeed responsible for reionizing the universe, we will finally see how their light sculpted space itself. The philosophical weight of this moment is difficult to ignore. For billions of years, the radiation from those first galaxies has been traveling through space, carrying not just information, but consequence. Without their light, the universe would have remained hidden in its own fog, its later structures unable to take shape. Every star that formed afterward, every atom that assembled into planets, owes its existence to that transition. In a literal sense, those early galaxies made the universe visible. And yet, for all their influence, they lasted only briefly. The same violence that ionized space would have consumed their gas supplies quickly. Within a few 100 million years, many of them likely faded, merging or collapsing into larger systems. Their light continues to reach us, but their bodies are gone, absorbed into the growing web of cosmic structure. They were architects and victims of the same transformation, lighting the way forward and burning themselves out in the process. The ionization era was not the dawn of calm, it was the universe's first storm. In that storm, gravity, radiation, and chemistry collided to create everything we now know. Webb's images, faint and red, are the raindrops of that storm reaching us long after the thunder has faded. Each one is a record of how darkness surrendered to light, and how the universe, once blind, learned to see itself. The LCDM model, lambda cold dark matter, has been the backbone of cosmology for nearly 3 decades. It explains the structure of the universe from the cosmic microwave background to the distribution of galaxies today with elegant simplicity. Roughly 70% dark energy, the mysterious L, or lambda, 25% dark matter, and 5% normal matter, the atoms that make stars, planets, and people. Within this framework, the universe expands at a predictable rate. Structures grow gradually under the pull of gravity, and time itself unfolds according to equations that fit almost every observation ever made. Until now, Webb's discovery has forced cosmologists into a rare moment of silence. The model, which once seemed unshakable, now appears incomplete. It is not that LCDM is wrong in principle. It still describes large-scale structure and cosmic expansion with precision. But its predictive power fails at the earliest times. The galaxies Webb sees should not be there. Yet they are, their light undeniable, their distances confirmed. They stand as quiet witnesses against a theory that can no longer account for all of reality. The crisis begins with timing. LCDM assumes that dark matter, being cold and slow-moving, takes hundreds of millions of years to clump into halos large enough to seed galaxies. Gas follows those halos, cools, and forms stars. This steady, bottom-up process should have produced a universe filled mostly with small, dim galaxies in its first billion years. But the Webb data shows large, bright systems dominating that epoch, each containing tens of billions of stars. The timeline is off by a factor of at least 3. The second issue is mass density. In the Standard Model, the total amount of matter available to form galaxies is limited by measurements of the cosmic microwave background. There simply isn't enough material early on to build hundreds of massive systems so quickly. For Webb's galaxies to exist, the universe must have condensed matter more efficiently than predicted, or gravity must have behaved differently under extreme conditions. Either way, the equations of LCDM need revision. Then comes the problem of brightness. These galaxies shine with luminosities far beyond what their inferred masses should allow. They are too efficient at converting gas into stars, too organized for their age, too mature for their time. In LCDM simulations, feedback from radiation and supernovae keeps galaxies from growing this quickly. But the Webb galaxies seem immune to such constraints, forming stars at rates up to 100 times faster than expected. The model's internal brakes are missing. It is as if the early universe forgot to obey its own limits. Some cosmologists respond to these contradictions cautiously, suggesting that the model might survive with slight adjustments, minor tuning of parameters, small modifications to feedback efficiency, perhaps even new particle interactions. Others see the problem as more fundamental. The discrepancies between theory and observation are too wide, too consistent, to be repaired with tweaks. The model might be a special case, accurate for much of cosmic history but inadequate for the beginning. In discussions across observatories and universities, a new phrase has started to appear: beyond LCDM. It carries both excitement and unease. The last time cosmology faced such a crisis was in the late 20th century, when the universe's accelerating expansion forced scientists to introduce dark energy. Now, another revolution may be forming, one born not from faint signals in background radiation, but from clear, defiant light at the edge of time. The proposed alternatives range from conservative to radical. One idea is that dark energy, the force driving the universe's expansion, might have behaved differently in the past. If it were weaker or even reversed in sign for a brief period, expansion would have slowed, allowing matter to clump more rapidly and form galaxies earlier. Another possibility is that dark matter isn't entirely cold. If a fraction of it interacts with itself or decays into other particles, it could produce small-scale fluctuations that seed rapid structure formation. A third idea questions the assumption that the early universe was uniform. Perhaps density variations were stronger in some regions, creating oases of early collapse while other areas lagged behind. Some physicists venture further, suggesting that the equations of general relativity, Einstein's great framework for gravity, might need subtle modification under the extreme densities of the early cosmos. In these modified gravity models, the force that pulls matter together could have been stronger in the beginning, tapering off as the universe expanded. That would naturally produce the fast growth Webb observes, while leaving the modern universe largely unchanged. It's a daring proposition, one that treads close to rewriting one of physics' most sacred principles. Whatever the mechanism, one truth is becoming clear. The early universe was more dynamic than anyone imagined. The simplicity of LCDM may have hidden a deeper complexity, a phase of accelerated creation, a storm of physics that burned out before leaving obvious traces in later epochs. If that is true, then our understanding of the cosmos resembles a film seen from the middle onward. The opening act, still partly hidden in infrared light, is more chaotic, more creative, and perhaps governed by different rules. For the scientific community, this moment is both unsettling and exhilarating. The challenge of reconciling theory with Webb's observations has triggered a wave of new models, simulations, and debates. Some will fail quickly. Others may survive to redefine cosmology. That is how science evolves, not through comfort, but through contradiction. What Webb has offered is not the collapse of understanding, but its renewal. The telescope has not broken the universe. It has broken our illusion of certainty. In private discussions, astronomers admit the emotional weight of this revelation. For decades, the LCDM model provided a sense of stability, a unifying story linking the Big Bang to the present. To question it feels like losing a map that has guided generations, but it also feels like standing at the frontier again, where discovery is possible and wonder is real. The galaxies at the dawn of time are not errors to be corrected. They are evidence that the cosmos still has secrets left to share. When the history of this century's science is written, the James Webb Space Telescope will not be remembered merely as an instrument. It will be remembered as a turning point. It forced humanity to confront the fact that even after 100 years of cosmology, we may still be at the beginning of understanding. The light that reached Webb's mirrors crossed almost the entire age of the universe to tell us a simple, humbling truth. The story we have told ourselves about creation is incomplete. The LCDM model will not vanish overnight. It will evolve, as all great theories do, adapting to new data, reshaping its assumptions, and perhaps merging with something grander. But the first cracks have formed, and through them, light is pouring in. Light from galaxies too old to exist, too bright to ignore, too beautiful to explain. And as those photons continue their long journey into our instruments and minds, they whisper the same message that has always driven science forward. The universe is not finished teaching us who we are. Every discovery in astronomy begins with light and ends with reflection. Long before the James Webb Space Telescope unfolded its mirrors, humanity had already written stories about beginnings, how the first stars lit the darkness, how galaxies emerged like embers from a cosmic fire. But when Webb opened its golden eyes and saw what lay beyond, it returned not confirmation, but contradiction. The universe we thought we knew had lied, or perhaps simply withheld the whole truth. And in that deception lay the most honest revelation of all. Creation was more urgent, more chaotic, and more wondrous than any equation could contain. The 300 galaxies Webb found are not just distant, they are ancient messages. Their light has traveled across nearly the entire span of cosmic history, crossing oceans of expanding space, losing energy, stretching into red. Each photon carries the memory of an impossible moment, stars burning in an infant universe that should have been dark. Together, they compose a single sentence in the language of physics. You have only begun to understand. What the telescope has shown is not just the past, but a mirror of the present. Science advances by believing it is close to completion, only to be humbled again by reality. Every generation of astronomers inherits the same surprise, that the universe is always one step ahead, rewriting itself as we learn to read it. The galaxies Webb revealed are proof that the cosmos still contains more imagination than we do. Somewhere in that red-shifted light, time and meaning intertwine. Those galaxies no longer exist as they did when their light began its journey. They have merged, evolved, or vanished entirely. Yet their light endures, a perfect record of what once was. The photons arriving at Webb's detectors tonight are older than our planet, older than the sun, older than the very atoms in our bodies. They began their voyage before Earth cooled, before life breathed, before thought existed to interpret them. To capture them now is to catch the past in mid-sentence, to witness history before it knew it was history. The implications stretch far beyond astrophysics. If the early universe could assemble complexity so quickly, then perhaps creation itself is not a process of patience, but of intensity. The cosmos did not wait for permission to build. It rushed headlong into structure, defying its own constraints. That urgency may be written into the fabric of existence, a reminder that even from chaos, order insists on emerging. Gravity, light, and time conspired to build galaxies against all odds, as if the universe were impatient to become conscious of itself. In laboratories and observatories, scientists now revisit their equations, adjusting, testing, and doubting. Some feel frustration, others, awe. For many, the paradox is not a problem to solve, but a privilege to witness. We are alive at a moment when the universe is revealing a secret it kept for nearly 14 billion years. To be confused by the cosmos is a form of grace. Future missions will peer deeper still. Spectroscopic instruments will dissect these galaxies' light, measuring the fingerprints of elements, the motion of gas, the presence of black holes. With each observation, we will refine our story, closing some gaps and opening others. That is the rhythm of knowledge. The closer we look, the less finished everything becomes. Webb is not the final word in cosmology. It is the beginning of a new conversation between light and understanding. And what a conversation it is! Through those faint crimson smudges, we see the universe as it was when it was only a few 100 million years old. But in those same photons we also see ourselves, creatures of stardust, trying to read our own origins from the glow of dying suns. The galaxies that shouldn't exist remind us that impossibility is often just a lack of imagination. What we call paradox may simply be the universe revealing that our questions are still too small. Perhaps that is the true legacy of the James Webb Space Telescope. Not that it photographed the earliest galaxies, but that it restored mystery to the cosmos. It reminded humanity that the universe is not a solved problem, but an ongoing creation, a story still being written in the language of light. Each discovery Webb makes is both an answer and an invitation, a chance to learn, to doubt, to wonder. Someday, new telescopes will look even further, tracing the first atoms as they came together, capturing the moment when darkness truly gave birth to light. They will build upon Webb's revelations, transforming today's astonishment into tomorrow's understanding. But even then, even when the data seem complete, there will remain something unreachable, a horizon beyond which the universe keeps its final secret. The light from those 300 galaxies will continue to travel, passing Earth, crossing empty space, moving toward no one. Long after our species is gone, it will still exist, carrying the record of a cosmos that once dared to break its own rules. And if somewhere, someday, another intelligence catches those photons, they will see the same defiance written in their wavelengths. That creation happened faster than expected, that beauty arrived sooner than allowed, that the universe could not resist becoming. In the end, that is the lesson Webb has given us, that the cosmos is not bound by our expectations. It grows, it surprises, it contradicts, and it endures. The galaxies that should not exist do exist, and through them, we glimpse not disorder but a higher coherence, one that transcends what we can measure. The telescope may orbit in silence, but the message it delivers is louder than any sound. The laws of the universe are not walls. They are invitations, and somewhere in that invitation lies the reason we look up at all.